Okay, hello everyone and welcome to this presentation, and this presentation is related to one of the papers at the 2021 IEEE Power Energy Society Innovative Smart Grid Technologies Latin America. And the title of this paper is Field Harmonics Measurements and Computer Simulation of a Static Voltage Compensator at the Mongolian Transmission Network. And the authors of this paper are Shoidor Adila Bazar, Marta Noemi Acosta, and myself, Professor Francisco Gonzalez. And this paper is a collaboration between the National Dispatch Center in Mongolia and the University of Southeastern Norway. Well, let's start this presentation with a short introduction. And as you must be aware, inside the electrical power system, there are several devices that they tend to modify the shape of the sine wave or the electricity supply. Those components, they have the possibility of creating nonlinearities and between relationship between voltage and currents and so on, and all those non-linear loads, they produce harmonic distortions. These harmonic distortions, they are very, very critical when we are talking about two important aspects. One of them is ensuring the power quality, the quality of supply that we provide to the customers, but at the same time, some of those harmonics pollution, some harmonics distortions, they have the capability of affecting the lifespan of the equipment. That is the very specific case of transformers and some other devices. Also, power harmonics is also one very interesting and very hot topic in recent time, especially because the development of the modern converter technologies. In this paper, we present the result of field harmonic measurements and also a computer simulation using a digital software of one static voltage compensator installed in the Mongolian power system, Mongolian transmission network. In this case, we are talking about specifically a 3-level voltage substation, 220, 110, 35 kV, Tavan Tolgoi. And that is one of important substations in the Mongolian electrical power system. And over there, we have a SVC, a static voltage compensator. In this case, we are using real harmonic analysis studies coming from measurement data in the electrical system. And from there, we are taking advantages of those measurements in order to implement digital simulations, okay? But let's start this presentation now, show you the location, the specific location of the measurement points and the instruments used here, okay? As you can see in this slide, on the right-hand side, you can see a single line diagram. You can see the external grid, and from there, there are a bus bar in 230, and over there, you can see the very important substation, 3-level level voltage substation, and you can see 230 high voltage side, 110 the low voltage side, and the tertiary of this 3-winding transformer, power transformer, is 35 kV. And in that 35 kV, you can see that that is the location for the static voltage compensator number 1. And in this case, you can see on the top right-hand side, the photo in winter of this substation and the location over there of those filters used for the static voltage compensation, okay? The measurement was selected to be at the terminal of 35 kV of this static voltage compensator, and this was a consequence of a noise that was audible during the operation of the static voltage compensator in the transformer T1, okay? And we realized that there is a potential issue with this big noise coming from the transformer, and we perform a series of measurements, okay? In this paper, we are limited on time and space, and we present just one of those cases, okay? The static voltage compensator installed in that 3 voltage level substation is basically a static voltage compensator that have a maximum capacitive reactive power of 30 MVAr and inductive power of plus 30, okay? And in this case, we are using a thyristor-controlled module, okay, reactance module. And in this case, let me go for the next slide. You can see here the configuration. We are using thyristors. In this case, we are using a 6-pulse thyristor for the TCR, okay? On the right-hand side, you can see the data. You can see the data for the main important electrical parameter for the TCR, but also for the harmonic filters for the third harmonics and the fifth harmonics, okay? In this case, we went to the substation. My colleague Shoidor, he went to the substation, and over there he records measurements using a very specific power quality analyzer, PQA. In this case, in a Chauvin R nodes CA8336, okay? In this case, this instrument is specifically designed for power quality analysis, reaching until the 50 harmonics, okay? Then, after we collected the measurements regarding active power, reactive power, voltage, currents, and frequency, well, we took that data in October 2020. It was a cold winter, and at the same time, the compensators, the filters for the third harmonic and the fifth harmonic, they were disconnected. Table number 2 show you the operating conditions at that moment in the static voltage compensator. Table number 3 present the classical standard for the requirements of harmonic currents in transmission system, and then depending of the harmonic, and then for the THD, okay? Then we took those measurements, okay? Over here you can see those measurements, and we insert those measurements inside the software DIgSILENT PowerFactory, okay? We use the whole model for the Mongolian power system. We are talking about 61 synchronous generator, 3 wind power plants, 6 photovoltaic system, and 3,685 terminals, and more than 230 transmission lines, okay? In this case, we introduced the 6 pulse thyristors at the substation, and we took advantages of the measurements. You can see here the harmonics measurements that we got. On table number 5, you can see the harmonic contains for each one of the voltage and current for ABC and ABC. And also on the figure number 8, you can see a bar plot of those harmonic contains, okay? Then we took those values and we run a simulation, and in this case we try to replicate the behavior of the measurements and then compare one-to-one those measurements, okay? We use the tool, the specific tool that PowerFactory is equipped for harmonics lot flow. And from there, well, we create a comparison. We create a comparison between the measurements and the simulate situation, okay? In those cases, we create the comparison. However, you can see that there are some agreements regarding the voltage and some THD deviation specifically for currents, okay? However, it's clear that the error was below 20% in the simulation in the worst case scenario, but almost all of them are around 5%, okay? What is the conclusion here? Well, we have the opportunity to go to the substation, go and take measurements regarding the power quality, specifically the harmonics. In this case, we collect the THD. The good news is that the THD at the static voltage compensator in Mongolia was below 5%. To be honest, was 2.53. That means that we don't have major problems related with THD at the static voltage compensator. Okay, The interesting thing here is that we have the opportunity to take real measurements and then compare the model that we have inside the DIgSILENT PowerFactory and compare the THD, and we got some decent results between the simulation and the real implementation. Finally, it's worth to say that we can with this paper we can ensure to the company that in this case the noise was not related with harmonic at this moment. However, a further assessment of that transformer was suggested. Okay, there are here some reference. You can go to the paper and read all those 11 references. And well, it's time for question and answers, and we are extremely happy to answer your questions. And that's all for this video. Thank you very much. Bye now.